Oh, hi, my name is Eric Jamois. Thank you for joining me in this ADMET Predictor interactive tutorial dedicated to HTPK. For reference and consistency with other tutorials, I'm using version 10.2 of ADMET Predictor, which is also known as APX.2. So our topics today will cover HTPK simulation. We will go through the calculation of %FA, which is fraction absorbed, %FB, which is fraction bioavailable. We will go through parameter sensitivity analysis, dose estimation, as well as the generation of CP time curves. We will also see how you can use experimental values as part of simulations. So there's a lot to cover, so let's get started. The HTPK tools can be found under tools and PK simulation. And you will see in the Lucas side menu here, %FA and %FB, dose estimation, CP time curve, and parameter sensitivity analysis. Now they're grayed out because I don't have any data set loaded. So they're also grayed out in the on the icons. So we have icons for %FA, dose estimation, CP time curve, and a parameter sensitivity analysis. So now we're going to load a subset of compound. It's actually a subset of the enamine diversity set of, I think the complete set has slightly over 10,000 compounds. So I took a 2,000 compound subset, which should be sufficient for the purpose of our work today. So I just opened this SDF file, and the first thing we're going to do is to calculate physicochemical properties for these compounds. So in order to do this, we're going to go into data and calculate ADMET properties. So we don't need transporters, metabolism, toxicity, or modeling descriptors. We just need the physicochemical descriptors. Actually, you don't need them per se to calculate HTPK parameters, because the software will run the models that it needs behind the scene in order to fuel the HTPK calculation. However, as you will see later, we will need these physicochemical properties as part of the analysis work that will ensue. So let's go ahead and calculate them. That's pretty fast. We've gone through this exercise before, and as we know, the software is multi-threaded, so it goes through this property calculation fairly quickly. So we get our properties calculated back to us, and now we're going to go into properly speaking HTPK. So we can just use this icon %FA and %FB over here, which sets up our calculation. So notice that there are two physiologies that are available, rat and human. You cannot calculate for both at the same time. It's either one or the other, and it is the same for the dosage form, immediate release tablet or IV bolus. It's one or the other, and we are going to select immediate release tablet for the purpose of this exercise. Now for doses, it's a little bit different. By default, the software has a 10 milligram dose entered. Notice that you can, of course, change that, but you can also enter multiple doses. So should we desire to run multiple doses, which we're going to do, we're going to take 1 and 100 milligram doses. You can just enter these two numbers separated by semicolon, no space. The other thing I want to draw your attention to is the fact that on this side menu here, if you had a column that contained different doses for each compound, you could point the software to this dose column, and the software would run. Of course, we don't have such a column here, but if you had a dose column, you could point the software to that specific column, and it would run a different dose potentially for each compound. That's a pretty useful option. So one of the strong premises of this program is that it can proceed entirely from structure or use a combination of experimental data and simulation. Okay. So here in this first run, we're going to go entirely from structure using the default settings. Okay. So in order to calculate fraction absorbed, so %FA and %FB, we have both checked right now, so it's going to calculate both, and again for both 1 and 100 milligram doses. And the only thing you have to do really to get this going is just to press the run button. So we're going to go ahead and do this. Now, just like other calculations we've seen in the software, these calculations are multi-threaded, so they likewise go extremely fast. We're running at over 100 compounds per second, and this is just a standard laptop computer. There's really nothing special about it. So here we go. So we get a number of columns output back to us. %FA for the 1 milligram dose, but if we look over to the side, we also have it output for the 100 milligram dose over here. So, so again, we have a duplicate output for the 1 milligram and 100 milligram doses. So we have %FB, again, fraction absorbed, %FA, fraction absorbed, %FB, fraction bioavailable, Cmax underscore HUM for human at the 1 milligram dose. That's what the 1 stands for. That's the Cmax, that's the maximum plasma concentration reached. Tmax is the time at which this maximum concentration is reached. Then we have AUC for the last dose, and also the AUC INF for infinity is the AUC from 0 to infinity. And then we have the estimated total estimated total clearance, and we also have at the end here the individual clearance terms. Okay, we have T1 half, so half-life, estimated half-life for the compound, and we also have the human volume of distribution that is used in the simulation. So there's quite a bit of output here, some very useful data, and I'm going to show you the kind of analysis that you can perform with this output. So it's nice to have data, but then you really have a lot of capabilities at your disposal to analyze it in a meaningful way. So one of the things that we can do very easily on this plot is to plot %FA at the 100 milligram dose against %FA at the 1 milligram dose. Okay. And what this is going to show us is on the diagonal, we're going to have the compounds for which fraction absorbed is concentration independent. Okay. And then the off-diagonal compounds are those for which fraction absorbed is concentration dependent. And to the extent that it is, the %FA at the higher dose of 100 milligram is always lower than the %FA at 1 milligram. Of course, the higher the dose, the lower the predicted fraction absorbed. So, and one of the things that we can easily do is actually color these compounds by solubility. And that's, now you see the reason why we bothered to calculate some of these physical chemical properties as part of this exercise, is because they become really handy later on to analyze your data. And if you do this, you will see that most of the compounds that are on this concentration independent diagonal are those that are predicted to have high solubility, whereas the ones that are falling sort of off diagonal, the concentration dependent compounds, or at least the compounds predicted to be concentration dependent, are those that may have solubility issues associated to them. So that's again a pretty interesting analysis that we can do. We can also show percent FA at a certain dose, percent FB as a function against percent FA. Again, we're not going to color by anything at this point. And actually, we want the reverse. So percent FA at 1 milligram versus percent FB at 1 milligram, and off we go. So what this is showing us here is, again, percent FB on the y-axis, percent FA on the x-axis, and what we see is that on the diagonal we have compounds for which there is not that much difference between percent FB and percent FA, meaning they're not metabolized a whole lot, because that's the difference between the fraction absorbed and the fraction bioavailable in this simulation, is there's the metabolism in between the two. So the more interesting compounds would be those that have both high fraction absorbed and high fraction bioavailable. And then we see that over here, for example, we have compounds that are predicted to have a high fraction absorbed, but there's likely a lot of metabolism activity that's associated to them, and that's to that extent why their fraction bioavailable is considerably less. So again, that's another way to look at these compounds. Another interesting plot maybe to look at percent FA. Again, we can take 1 milligram as a function of permeability. So this is for us the S plus PEF model. Okay, and we're not going to color by anything at this point. But so what we see is that compounds that tend to have higher permeability, and that's against our effective jejunal permeability model, those compounds that are predicted to have higher permeability, jejunal permeability, are also predicted to have a high fraction absorbed. Okay. But however, there are compounds that do fall out of this relationship, and again, if we color our compounds by solubility, we're going to put solubility on the log scale here, you will notice that the compounds that fall out of that general relationship are compounds that are predicted to have lower solubility, and those are referred to as solubility limited compounds. And now we can also do the opposite. So we can take percent FA against solubility, and we'll take that on the log scale, and then color by PEF. Okay. And we have a similar relationship where the compounds that are predicted to be more soluble do tend to have a higher fraction absorbed, but there are compounds that do fall out of this general behavior, and those are the so-called permeability limited compounds, which are shown here in red. So that is an interesting behavior. There's actually a very nice paper by Hendrickson and co-workers, which I will show briefly. And so it's by Hendrickson, Sanchez Felix, and our own Michael Bolger, who just retired from our company, was with us for, I think, over 26 years, and contributed to this paper, which makes a very similar analysis where you actually have the three-dimensional plot. What I showed you was essentially 2D projections of this plot, and then you have here the four classes of class 1 compounds that have both high solubility and permeability, class 2 compounds that have low solubility, which is limiting, and high permeability. Then you have class 3 compounds that are the reverse, low and limiting permeability and not limiting in solubility. And then you have compounds that are limited by both permeability and solubility, referred to as class 4 compounds. So again, what I showed you earlier in these plots that we can look again, this particular plot is somewhat of a projection of that graph. So I hope you found this interesting, and that actually brings us into the topic of parameter sensitivity analysis, because we saw that, again, some of these compounds could be either permeability or solubility limited. So we're going to see how we can analyze that in a little bit more detail.